So in first problem, they have given a meson is captured by proton to form hydrogen-like atom, that is muonic hydrogen. Then the radius of first Bohr orbit you have to calculate. Okay, so it's a very simple problem. I think you people have done this problem. So for any hydrogen-like atom or for any finite mass nucleus, what you have to do? First, you have to calculate the reduced mass. Here, that system is you have proton at the center, and mu particle is revolving around this orbit or around this nucleus. Suppose this is your nucleus, and that mu particle, the mass also given of that mu particle, and that was the mass of mu particle was 207 times the mass of the electron. And you know the mass of proton, that is simply 1836 times the mass of electron. So for this system, you have to calculate that reduced mass first. Okay, so reduced mass of this system will be simply mass of mu particle into mass of proton divided by mass of mu particle plus mass of proton. So in terms of electronic mass, it will be simply 207 times the mass of electron into 1836 times the mass of electron divided by 207 times the mass of electron plus 1836 times the mass of the electron. Okay, is it clear to all? You people have done this problem, right? So if you calculate that reduced mass, you will simply get around how much? Anyone? How much you will get? Anju? Karthik?
186. 186.03.
Very good, very good. Approximately you will get 186 times the mass of the electron. Okay, so approximately you will get 186 times the mass of the electron. So now you can calculate that radius of this system or first Bohr orbit, radius of first Bohr orbit. What you have to do? You know that formula, Rn dash equals to me by mu into Rn, where Rn is the radius of hydrogen atom, and for first orbit or first Bohr orbit Rn dash, it will be simply, if you substitute that reduced mass here, you will get 1 by 186 into the radius of first Bohr orbit of hydrogen atom, and that is nothing but 0.53 angstrom. So what will be the answer? What will be the answer? Anyone? So it will be around 0.285 picometer, right? PM, picometer. Okay. So the correct option will be A. Okay. Is it clear?
Yes, sir.
Okay. Then they have asked second problem. Shall I erase? Shall I erase? In the second problem, they have asked the wavelength of first line of Balmer series for same system, muonic system. Okay. Then how will calculate that wavelength? So for first line of Balmer series, that transition is happening from where to where? From n equals to 3 to n equals to 2. Right? This transition is the first transition of Balmer series, is not it? Or first line of Balmer series? For first line of Lyman series that we have discussed from n equals to 2 to n equals to 1. For first line of Balmer series, transition is happening from n equals to 3 to n equals to 2. And you know that formula. If you remember that So this will be your second problem. That formula I wrote 1 by lambda equals to, let us calculate first for hydrogen atom. So for hydrogen atom, that first line of Balmer series will be 1 by lambda equals to R times, where R is the Rydberg constant, into 1 by 2 square minus 1 by 3 square. Okay, where R is the Rydberg constant and its value is 1.09 into 10 to the power 7 meter inverse. Okay, is not it? So the value of Rydberg constant in is 1.09 into 10 to the power 7 meter inverse. So if you substitute it, the wavelength of hydrogen atom for first Balmer line, you will get this wavelength will be, if you substitute this value, you will get 6563 angstrom. But they have asked for muonic hydrogen. So you know there is a relation between the wavelength of hydrogen atom and for wavelength of finite mass nucleus atom. So you have that, we have system that is finite mass nucleus. So that relation, if you remember, I wrote 1 by lambda equals to R, and you have 1 by NF square minus 1 by Ni square. Now you see R is basically what? If you remember, R was minus E1 by Hc. Now for finite mass nucleus, the energy is how it relate? For finite mass nucleus, the energy is like proportional to mu by Me, right? For energy of finite mass nucleus, it depends on reduced mass. So of course there is a relation between the Rydberg constant and reduced mass. So basically you can write that Rydberg constant of finite nucleus is basically proportional to reduced mass divided by mass of electron. So what will be the answer? If you correlate it, it will be simply, if you correlate it for finite nucleus, that wavelength of finite nucleus or finite mass will be simply how much? So you see lambda is inversely proportional to R, and R is proportional to reduced mass. So it will be basically, if you calculate, you can write that wavelength for finite nucleus mass basically related to reduced mass, and that relation is basically Me by mu. Is it clear? Since lambda is inversely proportional to R, R is proportional to reduced mass or mu by Me. So you can say that lambda will be proportional to Me by mu. Okay. So this is for your finite mass nucleus. Okay. And you know, for hydrogen atom, H atom, it will be simply hydrogen atom, it will be simply proportional to mass of electron. Okay, now let us take, this is equation number 1, this is equation number 2. Is it clear? Dhruvi, is it clear? Karthik, Shekhar, is it clear? Anju?
Yes, sir.
So what I am saying, that for finite mass nucleus, that wavelength proportional to Me by mu, where mu is the reduced mass. And for hydrogen atom, that wavelength is proportional to simply Me. So if you divide these two equations, you will basically get lambda of finite mass nucleus will be equals to the lambda of hydrogen atom, divided by the reduced mass of the system, and there will be on Mu also here. And you know that you calculated this value for hydrogen atom, it was how much? Simply 6563 angstrom and you have that mass, reduced mass is how much? 186 ME, and that ME will be cancelled with that this ME. So wavelength for this system will be 6563 angstrom divided by 186. So how much you will get? Can you divide it? So wavelength of for this muonic hydrogen will be 6563 angstrom divided by 186. So if you divide it, you will basically get 35.3 angstrom. Is it clear? Is it clear, Shekhar? Is it clear? Shekhar, is it clear? Karthik?
Yes, sir.
Anju, clear?
Yes, sir.
Ruby? Is it clear? Is there any doubt? Shall I erase?
Yes, sir.
Okay. Now, next problem, if people do, how we'll do. So, problem number 3, the binding energy of muonic hydrogen. So, you have same system. So, what I have done, I have taken same system, and I thought how many questions can we ask from this. Okay. So now we have to calculate hydrogen that binding energy. So can you anyone please tell me the how much is the binding energy of hydrogen atom when the electron is in the ground state? How much is the binding energy? Karthik, how much is the binding energy? Suppose you have hydrogen atom, or you have electron in the first Bohr orbit of hydrogen atom. So what I am saying, suppose you have electron that is at the first Bohr orbit of hydrogen atom. So how much its energy? Minus
13.6 volt.
So the binding definition of binding energy, the amount of energy that is required to remove this electron. So how much energy is needed to remove that electron when it is revolving in the ground state of hydrogen atom? So that energy is needed how much? It will be if you give 13.6 electron volt to this electron, then it will be removed. So binding energy of hydrogen atom when it is at the ground state of binding energy of electron when it is revolving at the ground state of hydrogen atom, that binding energy is nothing but 13.6 electron volt. Just how much energy it has at negative sign, you have to give that much energy, positive energy, to remove this electron from the orbit or to make it free. Is it clear what I am saying? So binding energy will be positive sign. Please don't confuse with this. Okay. So binding energy will be positive. Binding energy means amount of energy required to release or remove the electron from the orbit. Okay. So for hydrogen atom, you know, when the electron in the ground state, it is the binding energy is 13.6. So if you know the energy of orbiting particle, if you know the energy of orbiting particle, then you can guess the binding energy. Suppose for electron, just now I said the energy, you know, from that you can easily say yes, the binding energy will be 13.6. So for muonic system, I have to calculate the energy of the orbiting particle, and the orbiting particle is here mu particle. Okay, so you know that relation. You know that relation, right? So energy for finite mass nucleus, that is En dash, is nothing but mu by me into the energy of electron at the hydrogen atom. Okay. So binding energy muonic hydrogen will be how much? So what I'll do? So when it is at ground state, then energy will be how much? E1 dash, and that will be mu. Just I have calculated that mu was nothing but 186 times mass of electron divided by mass of electron, and the energy of electron at the hydrogen atom when it is at ground state is nothing but E1. So if you calculate this energy, this is the energy of muonic particle when it is rotating or revolving around that proton at n equals to 1. So that energy is mu by me, where mu is the reduced mass of that system into the energy of electron when it is revolving at the hydrogen atom at n equals to 1. Okay, so mu will be cancelled, and you know this value. So if you calculate it, it will be 186 times minus 13.6 electron volt. Is it clear? Is it clear to all? Anju, is it clear? Dhruvi?
Yes, sir.
Okay. Now if you calculate, how much you will get? So if you calculate that energy of this particle, you will get minus 2530 electron volt. So how much energy is needed to remove this particle? Yes. Shekhar, how much energy is needed? So you got that energy of revolving particle, and that is minus 2530 electron volt. Okay, minus 2530. So how much energy is needed? Shekhar, can you please tell me? Ruby, how much energy is needed? Anju, how much energy is needed?
2530 electron
Exactly.
volt.
Yes, very good. So it has energy is this mass. To make it free or to remove this muonic particle from this orbit, you need this much energy plus 2530 electron volt energy. So that's why the binding energy of this particle will be EV dash, you can say, and that will be 2530 electron volt. So your correct option is C. Is it clear? Okay, is it clear? Please give
Yes, sir.
yes. Please ask me question, because from next class we'll increase that speed and we'll go to nuclear physics. Okay, whatever question you have you have in atomic physics, please ask me today. Shall I erase? Okay. Question number 4. So in that question, yes, the velocity of mu particle in the first Bohr orbit of muonic hydrogen. Again that same question. So we have proton at the nucleus and mu particle is revolving, and that orbit number is n equals to 1, and mu particle is revolving. So if you know that formula, velocity, okay, velocity for finite mass, and that will not change because velocity is independent on reduced mass. Just someone was asking that question. That's a good question. So Vn dash is nothing but nothing equals to Vn. It is independent on the reduced mass, and that will be Z alpha y n, right? And there will be on C also, Z alpha y n, and C is the speed of light. Okay, so for this you can say that only proton at the nucleus, so Z will be on, and alpha is fine structure constant, that is 1 by 137. C is the speed of light, and at first Bohr orbit means n equals to 1. So it will be alpha C, and you know the alpha C is how much? Alpha is how much? Alpha is 1 by 137. So okay, and it will be how much? So 3 into 10 to the power 8 meter per second divided by 1 by 137. So it will provide you 2.18 into 10 to the power 6 meter per second, and you can check it is the same speed when the electron is revolving around the nucleus of hydrogen atom. Okay, is it clear?
Yes, sir.
Okay. Shall I erase? Shall I erase?
Yes, sir.
Okay. How was the test? Yesterday test. It was good. You are comfortable in the test.
Yes, sir. It was good.
Okay. Everybody, Shekhar, how was the test? Karthik, how was the test? Okay. Next question. This is a really good question. A positronium is a shortly bound state of electron and positron. The energy difference between first excited state and ground state, and how they are related to the energy difference between energy difference of hydrogen atom. So for positronium, already shared that on positron sitting at the nucleus, and electron is revolving. Okay. So you have to calculate energy difference between first excited state and ground state. So first you calculate that energy expression for positronium. So again I will use same formula, En dash, that is energy for finite mass nucleus, and that will be mu by Me into the energy of hydrogen atom. And for this system, mu will be how much? Mass of positron into mass of electron divided by mass of positron plus mass of electron. And you know the mass of positron is equals to mass of electron. So if you substitute it, so yes, this is positron into, okay. So if you substitute it, you will get basically m square by twice of Me, and that will provide you mass of electron divided by 2. So reduced mass of this system you got. So if you substitute it here, you'll basically get the En dash or energy of positive, this bound state will be nothing but how much? Me by twice Me into the energy state of hydrogen atom. So it will be cancelled, okay, and basically you will get En by 2. So energy of positronium system is half of the energy of hydrogen atom, okay, or energy of this electron when it is in the positronium system will be half of the energy when the electron is revolving around hydrogen nucleus, okay. Shall I erase this part? Shall I erase? So if you calculate E2 dash, and that will be the energy of hydrogen atom at first excited state divided by 2. So first I am calculating that energy of positronium system for first excited state. First excited state means n equals to 2, and that will be nothing but the energy of electron at first excited state of hydrogen atom divided by 2. Okay, so suppose this is equation number 1. Similarly, for ground state it will be E1 dash, and that will be nothing but E1 by 2. E1 by 2. And let us take this is equation number 2. So if you subtract equation 1 from equation 2, you will get the answer of that question. So energy difference between first excited state and ground state of positronium will be 1 by 2 times E2 minus E1. And E2 and E1 here, the energy of electron of hydrogen atom at n equals to 2, and E1 is, so E2 is energy of electron at hydrogen atom for n equals to 2, E1 is energy of electron for hydrogen atom for n equals to 1. So you can clearly see the energy difference for this system, energy difference between first excited state and ground state will be half of the energy difference of hydrogen atom. So correct option will be C, okay. Is it clear to all? Is it clear to all?
Yes, sir.
Okay. Okay, next problem is 6. An electron collide with a hydrogen atom in its ground state and excite it into a state of n equals to 3. How much energy was given to that hydrogen atom in this inelastic collision? Okay, so how much energy is given? It's a very simple question. So that energy will be how much? Delta E will be nothing but, so in hydrogen atom, electron is at ground state n equals to 1. Suppose this is n equals to 2 and this is n equals to 3. So on electron at ground state of hydrogen atom, another electron is coming having some energy and is colliding with this electron that is sitting at n equals to 1 of hydrogen atom. So what will happen? This electron will give some energy to this electron and it will make transition from n equals to 1 to n equals to 3. So how much energy that is given by this electron to this in this inelastic collision? So this is an inelastic collision since there is a loss of energy of this particle. Okay, so how much energy will be given? It's a very simple, just energy difference between that n equals to 3 and n equals to 3. Sorry, n equals to 1. So delta E, that is energy given, that will be energy given okay, and that will be nothing but E2 minus E3 minus E1. Okay, so E3 minus E1 means minus 13.6 by 9 plus 13.6. Of course, the unit will be electron volt. Is it clear? So if you will calculate it, you will get 12.1 electron volt. Is it clear? So how much energy will be given? The energy difference between n equals to 3 state and n equals to 1 state. So that will be nothing but E3 minus E1, and E3 you know minus 13.6 divided by 3 square, that is nothing but minus 13.6 by 9 minus, and you already have minus of 13.6. So that will produce plus sign here and you will have that number 13.6 electron volt. So if you solve it, it's a very simple algebra, you will get 12.1 electron volt. So correct option again C. Okay. Next you have question number 7. So in that question, what they have asked, or what I have asked, how many different wavelengths would appear in the spectrum of hydrogen atom initially in the n equals to 5 state? So electron is basically where at n equals to 5 state. So you will have many more state here, n equals to 4, n equals to 3, you will have n equals to 2, and of course you will have n equals to 1. You will have n equals to 1. So electron is initially here, so it can make transition from here to here, it can make transition from here to here, it can make a transition from here to here, and I shared that formula, right? It can transition from here to here, it can transition from here to here, okay, it can transition from here to here. So it's a very short trick. There will be 10 lines. So how will do this? I told you that formula. So initially where it is at n equals to 5. So if the initial state is n, the number of emitted line will be, or the number of spectrum will be how much? N into n minus 1 by 2. Here n is 5, so 5 into 4 by 2. So it's a very simple question. So that will give you 2. 5 into 2 is 10. So total you will get 10 line. So there will be many transition. I have not drawn all the transition because we know that formula. Okay, we will not use or we will not waste any time because time is very important. Okay, so we know that formula, just we will use. We can draw that, but it will take time. Okay, there will be 10 transition, and all transition will have different wavelength or different energy, and that will provide you unique line in the emission spectrum. Okay, is it clear what I'm saying? Anju, is it clear? Dhruvi, is it clear? Shekhar, Karthik, is it clear?
Yes, sir.
Okay. Shall I erase? Shall I erase?
Yes, sir.
Question number 8. As question number 8 is very good question. So who has done this question? Question number 8. Anyone in the class? Who has done this question yesterday? Anyone in the class? You know that formula, that Rydberg constant for finite mass nucleus, and that is denoted by Rm. The Rydberg constant for finite mass nucleus, that is Rm, and that is nothing but the Rydberg constant for infinite mass nucleus divided by the Rydberg constant for infinite mass nucleus is denoted by R infinity divided by mass of, divided by 1 plus mass of electron divided by mass of nucleus. So Rydberg constant for finite mass nucleus is given by Rydberg constant for infinite mass nucleus divided by 1 plus mass of electron divided by total mass of nucleus. Please note this formula, it is important. Okay. Now what they have asked, or what I had asked, a mixture of ordinary hydrogen and tritium is excited and its spectrum is studied. Okay, so initially they were in the electron in that hydrogen and tritium, it was in ground state, but somehow I increased the temperature or I gave some external perturbation, so in electron make transition from lower to higher orbit. Now what will happen, that when it is at higher orbit, that electron is not stable, because every system try to get stable position, and for stable position the energy should be minimum, and that is natural phenomena. Everyone in the nature try to get stable position. Like you want job, that is because your life will be stable. I want to become a good teacher. Okay, so everyone in the nature try to get stable position. So similarly, when you are exciting that electron will not be stable at higher excited state. It will jump to lower state, and that will give you some spectrum line, or that will emit some photon, and this photon will have some line if you see that in the microscope. Okay. So it's a very simple question. So for they have asked H alpha line. H alpha line means first line of Balmer series. H alpha line means first line of Balmer series. So what they have say, the shift in the wavelength. So when both system excited, they will emit photon. So the shift in the wavelength for H alpha line. So for both system or both atom, I have to check the wavelength of hydrogen atom and wavelength of tritium atom for H alpha transition. And we know that formula, very famous formula, we already have learned, and that is nothing but the 1 by lambda is equals to Rydberg constant into, so first line of Balmer series means transition is happening from n equals to 3, so n equals to 3 to n equals to 2. So final state is 2, initial state is 3, right? So we can write it like 1 by 2 square minus 1 by 3 square. Since both hydrogen and tritium, both are isotope of hydrogen, right? Every people know this, right? Tritium means you have 3 nucleon, and when you are taking simple hydrogen, it means it will have only 1 proton or 1 nucleon. So for both system, you will have number of protons same, but they will have number of nucleon different, and that is the definition of isotope. So tritium is basically the isotope of hydrogen atom. So since both will have different number of nucleon, so definitely they will have different mass number or different mass of nucleus, and that's why they will have different reduced mass. So we have to introduce that concept of reduced mass, because that wavelength shift you are ultimately getting due to the change in the reduced mass of the system. So what I'll do, I'll take here the Rydberg constant for finite mass nucleus. So first let us take 1 by lambda h. Lambda h means simple hydrogen. For simple hydrogen, you know, this is that I'll discuss in nuclear physics also. This is known as ordinary hydrogen. Tritium means 1h3. So tritium means you have 1 proton but 3 nucleon. Okay. So for ordinary hydrogen, let us take that symbol for first Balmer line, that is 1 by lambda h. So here I'll take the Rydberg constant for this system, that is, let us take this is R of h, and these things will be constant, that is 1 by 2 square minus 1 by 3 square. Okay. So if you calculate it or if you solve it, it's a very simple algebra. If you solve it for lambda h, you will get lambda h will be how much? Anyone? So 4 square into 9 is 4 into 9, it will be how much? 36. So 36, and you will have 3 square minus 4 square, that will provide you 5. So 5 RH, since it is you will get 1 by lambda h equals to 5 RH divided by 36. So if you inverse it, you will get lambda h, and that will be nothing but 36 divided by 5 RH. Now, okay, this is your for hydrogen atom, and for tritium it will be same. Since the transition is again from 3 to 2, just you have to change R value. For tritium, let us take that symbol R of T. So this constant, this value will be fixed 36 by 5, but here you have to take R of T. Here you have to take R of T. So you got that lambda is lambda T. Lambda is nothing but, and let us take this equation is 2. So lambda h is nothing but 36 by 5 RH, and lambda t is nothing but 36 by 5 RT. And I said that for finite mass, that Rydberg constant is for infinite mass divided by 1 plus mass of electron divided by mass of nucleon. So RH will be basically R infinity divided by 1 plus mass of electron divided by mass of proton, because in hydrogen atom you will have only 1 proton. So mass of nucleon will be, or mass of the nucleus will be simply mass of proton. But when you are taking tritium, RT will be R infinity divided by 1 plus mass of electron. Here mass of nucleus will be simply 3 times mass of proton, because you know it has 3 nucleon, 2 neutron is there and 1 proton is there, and we know mass of neutron is almost equals to the mass of proton. So mass of the nucleus for this fellow will be, or for tritium will be simply 3 times the mass of proton. So if you substitute it, ultimately what you will get, or if you make that difference, so lambda h minus lambda t will be how much? Lambda h minus lambda t will be your 36 by 5 will be common. 36 5 will be common. Then you will have 1 by RH minus 1 by RT. 1 by RH minus 1 by RT. Now you just substitute that value of 1 by RH and RT, you will get that answer. So if you solve it, you will basically get 36 by 5 into RH. RH will be how much? I told you R infinity. So for finite mass nucleus, R will be R infinity divided by 1 plus mass of electron divided by 1 plus divided by 1 plus mass of electron divided by mass of nucleon. So that denominator part will go to numerator, because this is 1 by RH. So basically what you will get, 1 plus mass of electron divided by mass of proton. So RH will be R infinity plus and that part will come in numerator, and that is nothing but 1 plus mass of electron divided by mass of proton. Similarly, if you substitute this for RT, you will get 1 plus mass of electron divided by 3 times mass of proton, and you will have R infinity here also. Okay. So if you solve that, R infinity will be common, or 1 by R infinity will be common, so you will get 30 by 5 into 36 by 5 into R infinity, then rest of the part will be 1 plus mass of electron divided by mass of proton minus 1 minus mass of electron divided by 3 times mass of proton. So that 1 will be cancelled. Simply how much you will get? Simply how much you will get? So if you solve it, you will get 36 by 5. Shall I write here? Shall I erase this part? Shall I erase? Anyone? Okay. Okay. So this part will come basically 36 by 5 into R infinity. Then you will have how much? So mass of electron by mass of proton you can take common from this both term, and then you will have 1 minus 1 by 3, and that will provide you basically, that will provide you 2 by 3. That will provide you 2 by 3. Okay. Is it clear to all what I am saying? Shall I erase this part? Okay. Now you know the R infinity is basically how much? That is actually your standard Rydberg constant value, that is 1.09 10 to the power 7 meter inverse. And you know mass of proton is 1836 times the mass of electron. Just I will substitute here this value. Okay, if you substitute it, okay, then you will get lambda h minus lambda t, and that will be nothing but, I have calculated, you can check it, 2.38 angstrom. Okay. So correct option will be again C. Ruby, is it clear? Shekhar, Karthik, Anju?
Yes, sir.
Anju,
Yes,
is it
sir.
clear? Okay. Shekhar, is it? Karthik? Where is Karthik? Okay. Shall I erase?
Yes, sir.
Okay. Next problem is problem number 9. It's a very simple problem, right? Yes. So in problem number 9, in hydrogen atom spectrum, the ratio of longest wavelength in the Lyman series to that of Balmer series. It's a very simple question. So for Lyman series, longest wavelength will be lambda L, and that will be R into 1 by 1 square minus 1 by 2 square, right? Let us take, this is your equation number 1. For Balmer series, let us take lambda V, and that will be for longest wavelength, it will be R into 1 by 2 square minus 1 by 3 square, right? Let us take, this is equation number 2. Okay. So you have to calculate lambda L by lambda V. How will calculate? Let us divide equation 2 by 1, and that will provide you 2 by 1. If you do it, that will provide you lambda L by lambda V. That's a very simple question. If you should do this simple algebra, you will get 0.185. Okay, 185. Thanks. Yes, This will be your ratio. It's a very simple question, nothing is there. Okay. Now, question number 10. There is a typos here. The question number 10 is actually what? So, in that question, an accelerated beam of electron bombarded a sample of hydrogen, and that there will be no question here. The question is like the third line of Lyman series is emitted. The third line of Lyman series is emitted, then electron must have been accelerated through a minimum potential difference. That potential difference you have to calculate. Okay, so there is a typos this question that there will be no question here. The question is the third line of Lyman series is emitted. So the electron must have been accelerated through a minimum potential that you have to calculate. It's a very simple question. Shall I erase? So how will calculate this? Anyone? So it's coming from where to where? That electron is third line, right? Third line of Lyman series means from where to where? So electron is basically making transition from n equals to 4 to n equals to 1. So electron from here it is coming. Actually, electron initially here and is coming to here n equals to 4. Then it is what is happening? It is making transition, like it is making transition to here. Okay, and that is giving you third line of Lyman series. So how much energy is needed to shift this electron from n equals to 1 to n equals to 4? That energy is nothing but E4 minus E1. And electron is accelerating and it is getting that much of energy. So what you have to write? E into V. Where is the electronic charge? V is the potential difference, and that V potential difference you have to calculate. So it's a very simple question. So what you have to do? E4 means minus 13.6 by 4 square, that will be nothing but 16. Then you will have 13.6, right? And that unit is electron volt. This side you have electron volt, E into V. V is the potential difference. So that will be cancelled, and that potential difference you will get in terms of volt. So this side you have, left hand side you have volt unit, and that potential difference you have to calculate in terms of volt. Electronic charge will be cancelled, and it's a very simple calculation. Nothing is there. So V will be nothing but how much? 12.8 volt. Is it clear, Shekhar?
Yes.
Dhruvi, is it clear? Anju?
Yes, sir. Yes, sir.
Is it clear, no? Okay. Then you have 11 number question, and that question is really interesting. Anyone has done this question? 11, question number 11. Anyone has done this question? 11 number question. It's a really good question. In that question, what they have given: a hydrogen atom and a lithium double plus ion, both are in the second excited state, right? And they have angular momentum that is given small LH and small Li. So you have to check which one will have higher energy and which one will have higher orbital angular momentum. If you remember that angular momentum I wrote, if you see that expression for angular momentum for orbiting electron, that is NH cut, and you see it is independent on any charge, any mass, any atomic number, any mass number. So for hydrogen atom in the which excited state they have said? A second excited state, right? So second excited state means n equals to how much? 2, right? 3, right? Second excited state means n equals to 3, right? Ground state means n equals to 1. First excited state means n equals to 2. Second excited state means n equals to 3. So for hydrogen atom, they have given LH. For second excited state, it will be how much? It will be simply 3H cut. Similarly, for lithium plus also, that is given that symbol small l subscript li. Again, it will be how much? 3h cat, because it is independent on any quantity, just it is depend on principal quantum number. And for both particle or both system, you have, they are sitting at second excited state, means n equals to 3. So just you have to substitute n equals to 3 for both cases, we will get how much? Same value. Now let us check. So what is the conclusion? That Li should be equals to L of Li. Is it clear? So it's a very good question actually. People used to get confused by taking different entities. There is a confusion. Okay, but there should not be any confusion because it depends only n value. Okay. Now you know that energy expression for any system, En is how much? Minus 13.6 Z square by n square. So for hydrogen atom, for n equals to 3, it will be how much? Simply n equals to 3. For hydrogen atom, it will be simply minus 13.6 divided by 9, because for hydrogen atom Z equals to 1, and obviously that unit will be electron volt. Okay. Similarly, if you calculate for lithium E3, for lithium, it will be how much? Minus 13.6 divided by 9 into 9 electron volt. So that 9 will be cancelled, you will get simply minus 13.6 electron volt. Okay. Now if you take magnitude, because they have asked in terms of magnitude, so obviously it will have higher magnitude, because if you take mod E3 of lithium, you will get how much? 13.6 electron volt. 13.6. Okay. And for hydrogen E3 hydrogen, that will be how much? That will be simply 13.6 by 9 electron volt. And you can easily check that this mod or this value is higher than this. So what is the conclusion? Their angular momentum is same, but mod of E3 for lithium should be greater than the mod of E3 of hydrogen atom. Is it clear? Anju, Dhruvi, is it clear? Is it clear?
Yes, sir.
Okay. Next problem is very simple. So for they ask about de Broglie wavelength for electron in the nth Bohr orbit of radius r. So very simple, right? I already discussed this. So nothing is there. So question number 12. So you know that formula. So nothing is there. 2 pi r equals to n lambda. We already have discussed this. Okay. So correct option is A for 12 question. Okay. Now there is a confusion in question number 13. What is the confusion is here? In question number 13, what is the confusion? See, that interesting thing is there. The kinetic energy of an electron in the nth excited state of hydrogen is given. And that is how much? Question number 13. Kinetic energy is given how much? For nth excited state, that is given 0.25 electron volt. And what they have asked, the magnitude of potential energy of that electron in nth state. So I already told that potential energy for any particular state is minus of twice of kinetic energy. Okay. So if you substitute that, you know that kinetic energy for this state, so it will be potential energy will be how much? 2 into 0.25 electron volt. Okay. So very simple. So how much will get? Minus minus 0.50 electron volt. But what I have done, I have given a trick. I mean, there is a mystery is here, or hidden part is magnitude of potential energy. Okay, so what you have to take? You have to take magnitude, and you know magnitude means we have to take only absolute value. So if you take magnitude of this value, it is nothing but 0.50 electron volt. So whenever you are solving any question in competitive, please be careful. Okay, you might think that what I am doing 100% correct, but there is always some hidden part. Okay, please be careful. Okay, is it clear to all? Is it clear to all?
Yes, sir.
Next, you have question number 14. So question number 14 I already I have done, right? In the question in the class we have discussed this thing, and that answer also you know, right? Nothing is there. For X-ray we know that formula, or for K alpha X-ray you can say lambda is how they are related with atomic number, is inversely proportional to Z minus 1 whole square, right? So for molybdenum, for K alpha line they have given. So for Z minus 1, when it will be for K series, that screening constant is on, that's why it is Z minus 1 whole square. In general, Z minus sigma whole square. Okay. So for K series, sigma is on. So lambda is inversely proportional to Z minus 1 whole square. Now for molybdenum, they have given that wavelength, that is how much? 0.72 angstrom, and also it has mass or atomic number is given. And they ask for the wavelength of copper K alpha, same line you have to ask. Just so it's a very simple question we already have done. So lambda of copper divided by lambda of molybdenum will be how much, since they are inversely related. So obviously here will that atomic number will be molybdenum minus 1 whole square divided by atomic number of copper minus 1 whole square, and that atomic number was given 42, right? 42 minus 1 divided by 29 minus 1 whole square. Also that wavelength for molybdenum target was given 0.72 angstrom. So obviously this copper wavelength will be how much? 0.72 into this number 42 minus 1 divided by 29 minus 1 whole square. So very simple question. So approximate result is 1.5 angstrom. Is there any doubt till now? Is there any doubt? Okay. Then last question, question number 15. I asked that frequency of first and second ratio of frequency of first and second orbit, right? So second excited state I asked. So you know that relation between frequency. So 15 number question will be F is inversely proportional to 1 by n cube. So I asked the frequency, ratio of frequency for first and second, yes, first and second excited state I asked. So basically what you have to calculate, first and second excited state means F2 by F3, and that will be nothing but 3 by 2 cube. Because for first excited state n is 2, and for second excited state n is 3. So 3 by 2 cube means 27 by 8. Okay, is it clear? And last question, question number 16, we already have done in that class, right? That magnetic moment, is not it?
Yes, sir.
Yeah, we have done, right? So this is all about your atomic physics. I hope you people enjoy that atomic physics part. Now we'll not lose any time. We'll go to that nuclear physics and we'll do very nicely that part. Okay. So if you have any question regarding atomic physics, you can ask me now, or you have my contact number. Anytime you can ask me. Okay. Because we'll go to nuclear physics, and that will enjoy that part. That's a really interesting part, and we'll get few important question from there also. Okay. So if people have any question, if no, then I can stop here. Any question is there?
No, sir.
Okay.
Yes, sir.
Okay, then I'm leaving. Okay. Bye all. Okay.